Hey there! Welcome to my video. Today what we're going to do is we're going to see how do we apply summation notation to evaluate a series. And you might be saying, wow, this is a lot. I don't know what summation notation is, and I don't know what a series is, so let's jump into what those two definitions are just to start. First thing is we want to do is we want to define what a series is. What a series is it's when the terms of a sequence are added together, and that resulting expression is called a series. So for instance, take these two sequences here. If I add 2 plus 4 plus 6 plus 8, adding those numbers now turns it from a sequence to a series. And then of course there's two different types. There's a finite series, which will have a limited number of terms. And then we also have an infinite series, which is one that has these dots, dots, dots that continue without stopping. When we're talking about a series, there's an abbreviated notation called summation notation, sometimes referred to as sigma notation, and you may have seen this before. What summation notation looks like is it looks like a capital letter E or the Greek letter sigma. It's just an abbreviated way to write a series. The way this sigma notation or summation notation works is you have a function here, or a function rule that sits to the right. And then what you have is you have this index on the bottom, which means the first number I would plug into this function rule to get back the first term of the series would be the result of plugging in. So for instance, these two summation notations just represents these two series shown above. So here you can see if I plugged in 1 into this expression, I'd get 2 times 1 would be 2. After 1, the next number I'd plug in is 2. 2 times 2 would be 4. The next number I'd plug in would be 3. 2 times 3 would be 6. And then this would be the last number I'd plug in at the top. 4. 2 times 4 is 8. And you can see I'd add that result, and that would be that finite series. Here, the difference between these two is that I have an infinity on top, meaning that after I plug in 1, 2, 3, 4, I'd continue plugging in 5, 6, 7, 8, and continue without stopping. Let's take a look at a more concrete example to try to hit this concept home. Here what I want to do is I want to evaluate this series, and it's written using summation notation. So a couple definitions that we should know. First one is the 8. That's the upper limit of summation. What that means is that's the last number that I'm going to plug into this function rule here. The next thing we should know is that k, or the variable, is the index of summation. That means here the only numbers that I'll be plugging in for is k, and then the 4 is the lower limit of summation, meaning that's the lowest number that I'm going to plug in. So to evaluate this expression, first thing I want to do is plug in 4. So I'll have 3 plus 4 squared. Next number I want to plug in after 4 is 5. So the next piece will say 3 plus 5 squared. Because I'm eventually going to add all of these terms, because it's a series and not a sequence, I'll be using plus signs in between. Well, I plugged in 4, I plugged in 5. The next number I'll plug in is 6. This will say 3 plus 6 squared. After 6, the next number I'm going to have to plug in is 7. This will say 3 plus 7 squared. And then the last number I'm going to plug in is 8, because that's the upper limit, so that's where I should stop here. Now all I have to do is evaluate all of these pieces. 4 squared is 16, 16 plus 3, 19. 5 squared, 25, 25 plus 3, 28. 6 squared, 36, 36 plus 3 is 39. 7 squared, 49, 49 plus 3 is 52. 8 squared, 64, 64 plus 3 is 67. If I add all of these together, I've evaluated this series, and the answer is 205. So this whole expression here equals 205. Let's see if you guys can try one on your own. I'd like you guys to evaluate this series here using the summation notation. Okay, let's take a solution to this one. First number I'm going to plug in is 2. I'm going to say 9 times 2. Then the next number I'll plug in is 3. 9 times 3. Then 4. 9 times 4. Then 5. 9 times 5. And the upper limit of summation is 6, so this will be the last number I plug in, 9 times 6. If I evaluate these here, what I'm going to get are these following numbers, and summing those together, this series is equivalent to 180. Let's try one more. This one was a Regents question featured on the January 2012 Regents, number 30. See if you can evaluate this series here that's represented by this summation notation. This one here was a little bit tricky because I'm guessing a few of you probably made mistakes when it became to this negative sign outside of the variable n. What this means is, because I don't have the expression written like this, negative n to the fourth, it's different here. What I'm actually doing is I'm taking the power, or the value of n, to the fourth power, and then I'm going to make the result negative, not taking the negative power to the power of fourth. That can be confusing. So when I plug in 1 here, what it's going to say is negative, with 1 in parentheses to the fourth, minus 1. After 1, the next value I'll plug in is 2. That would look like this. And then the upper limit of summation is 3, so the last number I'll plug in is 3. Evaluating the first one, 1 to the fourth is 1, which will become negative 1. Negative 1 minus 1 would be negative 2. Here I'll take 2 to the fourth, which is 16. The negative sign in front makes it negative 16, minus 2, negative 18. Here, 3 to the fourth is 81. This would become negative 81. Negative 81 minus 3 would be negative 84. When I combine these like terms here, the result is negative 104. That can be pretty tricky. I'll have you guys try one more of these Regents questions. This one is multiple choice. Now that you're aware of the way this is evaluated, maybe you won't make the same mistakes this time you could have potentially made on the last one. Last thing we want to accomplish in today's video is we want to see, if I'm given a series, can I represent it using summation notation? If you look at what we did in all the past problems, what we had done was, given something written in summation notation, we essentially wrote out the series and then just sum them together. What we want to do now is kind of the opposite. I want to give you guys a series and see if we can write it using summation notation. Well, first thing to do is see if there's a pattern here among this series. I can see the terms here went up by 4. The following terms went up by 4. And if I pay attention and look to see if this repeats, I can see all these terms are going up by 4. Because all of these terms are going up by 4, I know this is an arithmetic sequence, and I can write the function part of the series or of the summation notation using this formula. All I need to do here is plug in the first term, which I can see is 8, and the common difference, which we just saw is positive 4, and I can figure out what's going on here. So let's plug in. I'm going to distribute the 4. I'll get 4n minus 4. When I combine like terms, 8 and negative 4 will become 4. This here would represent this expression if it was a sequence. However, it's not a sequence, it's a series, and I can tell it's a series because of these plus signs. So for that reason, I'm going to use summation notation, and I'm just going to put this function rule here. Now I just have to decide what was the lower index and what was the upper index. Well, here I can see I had an 8 was the first term I plugged in. Well, what number, if I plugged it in for n here, would I get back 8? I suspect 1. 4 times 1 is 4, plus 4 is 8. So the lower limit of summation will be 1. And then I count, if this was plugging in 1, here I plugged in 2, 3, 4, 5, and for the last term, 28, I plugged in 6. So my limits would look like this. I choose r equaled 1 here. That should probably be n, since I used n up here. These should just match, but I could use any letter I want. Let's see if you guys could write a series using summation notation, provided a series. See if you could write the following series using summation notation. For this one here, it's a little bit challenging because there's negative signs and we're used to plus signs in between. So for a moment, I'm just going to imagine that these are all separate terms here and kind of see what's going on. Meaning if these were separate terms, they would be separated by plus signs. Well, let's see. To get from 2 to negative 5, I subtracted 5. To get from negative 3 to negative 8, I subtracted 5, and that pattern continues. So I can see here the common difference is minus 5. The first term is 2. plugging that into my arithmetic sequence formula would look like this. The first term is 2, common difference minus 5. Distribute the minus 5, combine like terms. Here I have my function rule for my series. Now all I need to do is find the bottom index. I suppose the bottom index will probably be 1, but let's check. If I plug in 1 here, negative 5 times 1 is negative 5. Negative 5 plus 7 is indeed the first term of 2. So down here, my lower limit will be 1. If this term represented plugging in 1, this one was 2, 3, 4, 5, 6, and my upper limit will be 7. This here represents that series. Let's do one last question. Here's a Regents question featured on the June 2012 exam, which asks which summation represents the following series. Well, thanks for tuning into my video. I hope this helped answer all of your questions on summation notations and series. See you next time.